Hi class, this is Mr. Morris, and in this video we are talking about periodic trends of elements. So what I want you to know before we really get started into this is what a periodic trend is. We are following up to the notes on the periodic table, and you learned a few of these periodic trends. What we mean when we say a periodic trend is what's the tendency of what happens as we go, let's say, from element number 21 to element number 24. Okay, so if I'm comparing scandium and chromium, if I'm going across the row from left to right, what tends to happen? Does it get bigger? Do the atoms get bigger? Do they get smaller? Do they hold their electrons tighter, or do they let go of them more easily? Just that's kind of the idea, the general idea. Or in the same way, what happens as we go down a column? Okay, so if I were going from lithium, let's say, to cesium, and comparing those two, which one's bigger, which one's smaller, and so on. We're going to learn how to compare atoms using the periodic trends. It doesn't mean that it's always true, but these are tendencies, and they're usually true. So, periodic trends are how properties of elements change across a period or down a group, and it depends on how protons and electrons in the atom interact with each other. Very important concept. Coulomb's law explains how charged particles interact with each other, and you probably basically know Coulomb's law without even knowing it, but we want to be a little more specific than what you already know. You know that opposite charges attract each other. That's part of Coulomb's law. The other part is like charges repel each other. So opposite charges, that's like positive and negative. Like charges, if it's positive and positive or negative and negative, they repel each other. When the charge's magnitude is higher, the attractive or repulsive force will be stronger. So what I mean by the magnitude is, let's say that I have a 1 plus charge and a 1 minus charge. Those are going to be attracted to each other, right? But if I have a 2 plus charge and a 2 minus charge, those are attracted to each other even stronger, okay? So these two have a stronger attraction because the magnitude is greater. We'll spend some time talking about that, but I just want to make sure that you understand the magnitude means like 1 plus compared to 2 plus. When the charge's magnitude is lower, the opposite would be true. The attractive or repulsive force would be weaker. This relationship is directly proportional. So if the magnitude is greater, it's a stronger attraction. If the magnitude is lower, it's a weaker attraction or repulsion. When the distance between the charges is larger, the attractive or repulsive force will be weaker. This is maybe kind of sounds counterintuitive, but if you think about magnets, it makes sense. So think about a magnet. If you're holding two magnets apart, and you're holding them at arm's length. Let's say you hold your arms apart as far as you can. Even if it's a pretty strong magnet, you can't really feel the force of attraction or repulsion between them. But as you draw them closer and closer and closer together, you start to feel the attraction or repulsion more and more strongly. And the place where you feel it the most strongly is right before they touch, when they're very, very close. So when the distance is larger, the attractive force is weaker, and when the distance between the charges is smaller, the attractive or repulsive force will be stronger. And we're talking about the distance between them. This relationship is inversely proportional. Now, when we're talking about periodic trends, we're referring to atoms, and atoms are made up of the nucleus, which is positive, and the electrons on the outside layer, which are negative. So when I say distance between the atoms, the biggest thing is if you have more energy levels. Remember, every energy level is like adding a new layer of electrons. And every time you get a new energy level, the electrons get farther away from the nucleus. So our distance gets greater as you get more and more and more electrons. Every time we add a new proton, that is actually increasing the magnitude of the charge. So we're going to look at the reasoning process for how to determine the periodic trends, and it's going to basically focus on those concepts we just now talked about. Here's our reasoning process in order of importance. So I've got these numbered for a reason. All right, we've got number 1, number 2, number 3, and number 4. It's because if number 1 is different, we don't even think about number 2. All we talk about is the first difference. If number 1 is the same, then we have to look at number 2. Okay? So if the number of energy levels is different, that's all we're going to talk about. If the number of energy levels is different, then we look at the form of logic that's over here. More energy levels means that you have a greater distance between the nucleus and the valence electrons. That's what I just said a little bit ago. If you add a new energy level, the electrons are farther from the nucleus. And if you have fewer energy levels, that leads to a smaller distance between the nucleus and the valence electrons. By the way, with that same logic, we could say more energy levels means a weaker attraction to the nucleus. Okay, so you might want to add that right here. Weaker attraction. Or just make a note of it in your mind if nothing else. You don't necessarily have to add that. But if we have fewer energy levels, then those would be closer. The electrons are closer, which means there's going to be a stronger attraction. And I want to really, really stress this set of notes. This part that we're doing right here, it's very important. It's the foundation for everything else that we're doing in these notes. So make sure that you don't skip over this. Okay, so what if we don't have a different number of energy levels? Oh, and by the way, if it's a different number of energy levels, that means we have, they're in different periods on the periodic table. Okay. If they're the same, then we would say this is if they're in the same period or the same row. If they're in the same row, then we have to look at our next form of logic, which is looking at the number of protons in the nucleus. If they are different, we're going to use the logic that's listed over here. If you have more protons, that leads to a stronger attraction between the nucleus and the valence electrons. And that, because we have a stronger attraction, that means that those electrons on the outside, which is what defines how big the atom is, those electrons get closer, so the volume of the atom or the size of the atom gets smaller and our atomic radius shrinks. So this decreases the distance between the nucleus and the valence electrons. If we have fewer protons, that leads to a weaker attraction between the nucleus and the valence electrons. So fewer protons, it means that there's not as strong of an attraction between those electrons on the outside and the protons in the middle. You've got a smaller positive charge attracting those outer electrons. And that increases the distance between the nucleus and the valence electrons. This is if it's a different element. It's still in the same period, but it's a different element. That's why it has a different number of protons. But if it has the same number of protons, that means it's the same element. So the only thing that might be different is its charge, or the number of electrons. So number 3, the last thing we could maybe compare is the number of electrons. You only use this if it's the same number of protons, so it's the same element, and the same energy level. That's the only time we're going to use this logic comparing the number of electrons. If the number of electrons is different, and that's the only thing that's different, more electrons lead to stronger repulsion among the valence electrons. Remember, electrons are like charges. So we have an electron and another electron. They are going to repel each other. They want to spread out. They repel each other. And if you have more electrons, that repulsion increases, and it increases the size of the electron cloud because they want to spread out. If you have fewer electrons, that leads to weaker repulsion among the valence electrons, and that decreases the size of the electron cloud. So as you're looking at this, if you have more electrons, they spread out more. You have fewer electrons, but the same number of protons and the same number of energy levels, they're going to spread out less, which makes it smaller, and those electrons are more tightly held. Okay. If there's a little bit of electron-electron repulsion, that actually makes the attraction lower. Remember, repulsion and attraction are kind of opposites. So you have more repulsion, that's less attraction. If it's the same, you have the same number of energy levels, the same number of protons, and the same number of electrons, then you have the same element. And all of the trends should be the same. They should have the same radius and all of the other things that we talk about. All right, that kind of sums up this first little bit. The next video, we're going to talk about the properties and do a couple examples.